Welcome to day 16 of Advent of Code, where the floor will be lava. Let's hunt for 2 more stars. A beam of light travels through the lava production facility and starts hitting various mirrors and splitters. The mirrors and splitters are provided to us in a 2D grid as shown below, where the dots are empty spaces in the facility. The beam starts in the top left corner and travels east. Any position in the grid becomes energized as soon as one or more beams of light pass over it. Given the map, we can determine how the beam bounces and splits. How many tiles end up being energized? Here is an example of the behavior of the mirrors. They are represented as forward and backward slashes, and hitting them from either side causes the light to bend 90 degrees as shown in these diagrams. Splitters are vertical bars and horizontal bars. If a ray of light hits a bar along its main axis, then it passes right through. If it hits a bar from either of its sides, then the ray splits and comes out in 2 opposing directions. Given the problem description and these examples of how the light will interact with the symbols in the grid, can you already solve today's part 1? Let's go on and have a look at the solution. On a high level, we, of course, just have to cast the ray and trace which unique fields are energized. So in our solution outline, we parse the grid and we collect all states that we see during our simulation that's triggered by the raycast function. Then, from these states, we'll extract the unique positions. The number of those positions is the answer of part 1. Now, before we look at the raycast function, we should understand what these states are. Basically, we're looking to encode the position and direction of a ray at any given point. The image shows a ray at the center of the grid, traveling east. Then let's cast some rays. Doing this raycast is basically a breadth-first search, as we keep expanding the rays as they travel across their paths. We use the scene states variable to prevent loops from occurring. Then, in the algorithm, as we've also seen on a few other days as well, we'll maintain a queue. In there, we will store the first state, which is position 0, 0, with a character indicating that we are traveling east. This is our starting position. Then, while our index I is smaller than the length of the queue, we get the state that's up next, and we increment I to simulate our first in, first out behavior. Then, if this state was not yet seen, we'll mark it as seen. Then we need to grab the symbol from the grid, which can be a dot or any of the mirrors or splitters, and we use that data to get the next states. If there are any next states, because this function might return an empty list, then we extend the queue. Before we look at how to get the next states based on the current state and symbol from the grid, let's take a step back and make sure that we understand why loops are a risk. Suppose we have this subsection of grid, and the beam of light comes in from the left, then on the right it will hit the splitter. From here we can hit the 4 mirrors in the corners, and theoretically the beam will go around and around. Many states here will overlap, so we'll track them in the seen states list, and we only expand rays that are in states which we haven't seen before. Getting the next states can use some convenience variables to make our code more easy to digest. First up is some directions which are indicated by a column or row shifts of 1 unit in either plus or minus direction. Then the following dictionaries help us to make some nice mappings in the next function. At the top, we want to be able to get any of the offsets from the previous slide and change it into a directional symbol via offsets to aim. Secondly, the trivial case what happens to a ray when it travels on a tile with a dot symbol. Here the up symbol just represents the logical offset. For instance, seeing the up arrow just means we keep going up. Then we have the diagonal down and diagonal up dictionaries. This, for instance, means that if we hit the backslash when coming in from the bottom, then we change our direction to the left. If we hit it from the left, then we go down, etc. Finally, we combine them into one big offsets dictionary. Then in the end, the getNextStates function can look as follows. It takes in a state and a symbol as we've seen before, and we return a list of new states. Let's first look at the end of the function, where we are in the scenario where we are not hitting any splitter. Why? Because splitters are potentially a special case where we end up with more beams coming out than we put in. So we did not hit a splitter, and we're either traveling through open space or we are hitting a mirror. So we get the offset based on the symbol in the grid, which got passed to this function, and the aim or direction of the current beam. Then we update our next aim because we store this in the state and we apply the offset. Finally, we check if the next position is actually in the grid, and if it is, we return a list with this new state. Otherwise, we return an empty list as there are no valid next states. Now, for the special cases where we hit a splitter. We first must determine whether we are hitting the splitter from the side or not. If we are, then we can recursively call the getNextStates function, where we pretend we're hitting mirrors instead. This allows us to bend the light in two directions easily upon hitting the splitter. If we're not hitting the splitter from the side, then the behavior is the same as passing through empty space. So here we recurse as well, and we simply pretend that the symbol in the grid is empty space instead of the splitter. And that's it for getting the states. Next up is getting the unique positions from the set of seen states. All this requires us to do is to loop over the states and only keep the positions. Storing them in a set gives us the total unique positions, and we have our answer for part 1. Let's move on to part 2. Apparently, the current starting position of the beam is not the most efficient, and we have control over that position. So we can align the beam with any position along the edge of the grid. If we search for the optimal initial starting position with the most number of tiles energized, then how many tiles are energized in that configuration? Since there is no fundamental change in behavior requested, let's go straight to the solution of part 2. What we have to do is start at all possible starting positions. Then we pass that start to the raycast function and we count the total unique positions again. In the loop, we can make sure to track the maximum number of positions as we loop over all possible options. Getting all possible starting positions can be done as follows. Just for every row, start on the left and cast to the east, or start on the right and cast to the west. The same works for the top and bottom rows. All that's left to do then is to pass the start to the raycast function, and we put it as the starting element in the queue. And then we're complete again. 2 more stars in the bag. Thank you for sticking around. Please subscribe, and let's prepare for tomorrow's problem.